In order to model the evaluation and behavior of dynamic system over time, there can be two cases. The variable time can be thought of a continuous variable or a discrete variable. In case of time being a continuous variable, the model may take the form of a differential equation, and for time as a discrete variable, the mathematical formulation often leads to a difference equation. So difference equations contribute towards the discrete mathematical models. Very often discrete models can be used as approximations for continuous model, and in fact discrete models become preferable in certain situations. A general difference equation of first order is of the type f xn plus 1 comma xn comma n equal to 0. Depending on f being linear or nonlinear function, the difference equation would be referred to as a linear or nonlinear. Nonlinear first order difference equations have got a wide application in various fields of life sciences, engineering, physics, social sciences, etc., wherever there occurs dynamics. Restricting our focus to economics, it has been observed that nonlinearity, stability and equilibrium are all related. Though the available literature is evident of the fact that more research has been done in the area of linear difference equation in economics rather than the nonlinear part. One major reason for this is because nonlinear difference equations have got no direct solution techniques as linear difference equation. Though fixed point analysis, stability behavior and approximation to linear difference equations are among some of the available investigative strategies for the study of nonlinear difference equation. Day and Schaffer in 1992 illustrated that a model can exhibit chaos in the presence of nonlinearity. In that case, prediction is not recommended, which is otherwise very often practiced in economic studies. In models like logistic growth model, nonlinear equation occur in discrete versions, and it becomes a question of importance to investigate the solution to the system, analyze them in the presence of nonlinearities, to study these equilibrium, etc. In this model, we focus on mathematical models of dynamical systems involving nonlinear difference equation and try to study their behavior and investigate such systems.
After reading this module, you shall be able to identify a first order nonlinear difference equation and classify it as homogeneous or non-homogeneous, solve particular type of nonlinear difference equation by linearization, study the qualitative behavior and analyze various aspects of nonlinear difference equations, apply the concept of nonlinear difference equation to economic models. A general first order difference equation is of the form f xn plus k comma xn plus k minus 1 comma n which is equal to 0. Here, if f is a linear function of its variable, then the difference equation is said to be linear. Otherwise, the above equation represents a nonlinear difference equation of first order. In other words, if all the terms appearing on the left-hand side function f are in the first power of its variables, or equivalently independent of products of variables and higher powers of variables, then the difference equation is said to be a linear difference equation, otherwise a nonlinear difference equation of first order. In our first method to analyze first order nonlinear difference equation, we follow an easy approach which is fairly applicable in general condition. This method is based on the graphical approach involving phase diagrams and is useful for the qualitative analysis of a difference equation. For a first order nonlinear difference equation, we can always write the given equation in the form xn plus 1 is equal to fxn, where f is a nonlinear function of xn. We now consider a Cartesian plane with xn and xn plus 1 as the coordinate axis. Plotting the two variables xn and xn plus 1 against each other results in a diagram called the phase diagram, and the curve corresponding to the function f is referred to as a phase line. We now analyze the time path of variable xn for various n by the process of iteration. In the phase diagram, xn plus 1 would be placed on the vertical axis along with the plot of the function f with respect to the variable x1. A 45-degree line or a straight line xn plus 1 equal to xn would be plotted in the phase diagram, as this straight line would be of great help in carrying out the graphical analysis of a difference equation to study its qualitative behavior. To apply this particular method, we need to be given an initial value first before the iterative process can be duly started. We consider four different phase lines F1, F2, F3, F4 as shown in the phase diagram. Using a 45-degree line in each of the phase diagrams, we mark the point x star on the horizontal axis obtained by intersection of the curves Fi, where I is equal to 1 to 4, and the straight line. Now mark the given initial value xo on the horizontal axis. Now from the phase line we know Fi maps initial values xo into x1 obeying the equation x1 is equal to Fi xo. So drawing a vertical line straight up from x star to the phase line Fi and reading the ordinate of the corresponding point on the vertical axis, we get the value of x1. Now using x1, we can get the value of x2 as x2 is a function of x1. For this, we transplot y1 from the vertical axis to the horizontal axis, which can be easily done by using the 45-degree line. That is, by making use of the fact that xn plus 1 is equal to xn. This means we simply need to mark the corresponding abscissa of x1 on the line xn plus 1 is equal to xn. From this abscissa, we again need to draw a vertical line to the curve f1 and find the corresponding ordinate, which is now x2. Repeating the same procedure with x2, we get x3 and so on. So to sum up, we can observe that the desired iteration can be achieved by simply following arrowheads from xo to point on phase line, then to the point on straight line, then to the point on the first phase line, and so on. In short, the path always keeps alternating between the phase line and the straight line, and not resorting to the coordinate axis is ever required. Next question that comes to mind is that what can be inferred from these time paths traced? The answer to this is that by this technique for a given initial value xo, this would determine if the pattern of change traced according to the phase line will lead to the intertemporal equilibrium value x star consistently or would go away from it. Let us now analyze all four different phase lines one by one. Clearly, the phase line F1 has a positive slope less than unity. Now, starting from the given initial value xo, as the iteration progresses, it leads to the intertemporal equilibrium value x star in a steady path consistently without oscillation. Also, if xo is placed to the right of x star, again there would be steady movement towards x star, now from the leftward side. So these time paths would be co-convergent to equilibrium. For the phase line F2, again the slope is positive, but more than unity. The initial value xo taken in this case is greater than x star, and the time paths lead away from the equilibrium value steadily. Also, if an initial value lower than x star is taken, similar divergent movement can be observed in the opposite direction. Now let us consider phase line F3, which is negatively inclined with a slope in between -1 and 0. In this case, the steady movement leads to oscillation. That is, in one iteration, the value exceeds x star, in the next it falls short of x star. In such case, as the absolute value of the slope of f is less than 1, the extent of overshooting diminishes as the iteration progresses, and so ultimately the path converges to the equilibrium. For the last case, phase line F4, the slope is negative and less than -1. The path shows an opposite behavior, that is, gradually it traces a divergent path. So in all, it can be inferred that the algebraic sign of the slope of the phase line determines if there will be oscillations, and in that case, the absolute value of its slope determines convergence or divergence. Hence, this graphic iterative and analysis an easy method that can be employed to the study the behavior of nonlinear difference equations, but of course, an initial value must be given to start with. However, there may occur many complicated cases where this technique may become a bit tedious to apply. In our next method towards analysis of a nonlinear difference equation, we examine the behavior of equation about its fixed point. Let us first recall the definition of a fixed point for a difference equation. A point is called a fixed point of a difference equation. Xn plus 1 is equal to a function of fxn if f x star is equal to x star. Xn plus 1 is equal to xn is equal to x star. So for a fixed point x star of a difference equation, the equation remains the same at x star for all subsequent iterations. Fixed points are also called equilibrium points of the system. Geometrically, as a fixed point occurs when x star is equal to fx star. So if we draw curves xn plus 1 is equal to fxn and line xn plus 1 is equal to xn on the same coordinate system, the point of the intersection of these two is the fixed point. Next to investigate is the nature of fixed points obtained. It is particularly important to investigate stability or instability of fixed points or the equilibrium points. Consider the system xn plus 1 is equal to fxn with x star as the equilibrium point where f is continuously differentiable at x star. Then 1 x star is an asymptotically stable fixed point, that is attracting fixed point, if f dash x star is less than 1. Second, x star is an unstable fixed point or a repelling fixed point if f dash x star is greater than 1. And third, if f dash x star is equal to 1 and if f double dash x star is not equal to 0, then x star is an unstable fixed point. B, f double dash x star is equal to 0, and if f triple dash x star is greater than 0, then x star is unstable. C, if f double dash x star is equal to 0, and if f triple dash x star is less than 0, then x star is asymptotically stable. The stability and instability of fixed parts can also be interpreted geometrically using the same graph by which the fixed point were obtained. We again go back to the geometrical evaluation of the fixed point, which was obtained as the point of intersection of using xn plus 1 is equal to fxn and xn plus 1 is equal to xn on the Cartesian plane with xn plus 1 and xn as the coordinate axis. To test a fixed point for stability, we start from a point on each side of the fixed point. In case there is more than one fixed point, we pick the point between the fixed point in test and the next nearest one. From the point chosen, we draw a line segment vertically to the curves xn plus 1, which is equal to fxn. The point where it intersects the curve, we move horizontally to the line xn plus 1 is equal to xn. From this point again, we move vertically to the curve xn plus 1, which is equal to fxn, and again horizontally from this point to line xn plus 1, which is equal to xn, and so on. If this path converges to the fixed point and so does the path formed from the point on the other side of the fixed point, then the fixed point in question is said to be stable or attracting. Otherwise, the fixed point is unstable. We restrict ourselves to inferring that the fixed point is unstable. Otherwise, unstable fixed point can be analyzed further for variety of their behavior as a period, chaotic, etc. In analytical terms, it can be interpreted as if x star is a fixed point and x naught is chosen arbitrarily, and if successive iterations would lead to its conversion to x star, then x star is stable fixed point, that is xn limit from n to infinity is equal to x star, where x naught is arbitrary. Example 1. We consider a non-linear difference equation xn plus 1 is equal to fxn, whose plot along with the line xn plus 1 is equal to xn is shown by the following figure. Here f dash x star is less than 1. Since the path traced vertically and horizontally from the arbitrary values x naught and x1 converges to the point x star, therefore x star is an asymptotically stable fixed point. Example 2. Next, we consider another example with the plot of the difference equation xn plus 1 is equal to fx and the line xn plus 1 is equal to xn given as follows. If we choose the arbitrary point x naught to the right of the fixed point x star, then tracing the path vertically and horizontally as discussed, we see that the path never converges to the fixed point. Hence, the fixed point x star is unstable. In this section, we consider homogeneous first-order nonlinear difference equation. The general equation of such form is fxn plus 1 xn n is equal to 0. Now, such an equation in xn can always be expressed in the form fxn plus 1 by xn comma n is equal to 0, equation 4. We use a transformation un is equal to xn plus 1 divided by xn, and if the function f is a polynomial function of xn plus 1 by xn, then 4 can be rewritten as product I from 1 to k in bracket un minus ai of n, which is equal to 0, where ain is the known function of n and k is the order of polynomial function in un. The solution to this system are often obtained by solving un minus ai of n is equal to 0 and xn plus 1 minus ai of n xn is equal to 0, which is equation 5. Each of the k solutions obtained from 5 provides a solution to equation 4. The solo growth model is known as a model of capital accumulation in an economy in which there are no prices and the economy is a pure production economy. The basic assumptions are: one, that the whole population works all the time with population growth rate n and each individual is assumed to supply only one unit of labor at times t. Second, a fixed proportion of the income is saved. Third, no taxes, no trade. Fourth, no prices indicate no financial market. Let nt be the population size at time t with constant rate of growth n. Nt plus 1 is equal to 1 plus n nt. Let the production function of firm be ot, which is equal to act raised to the power of alpha nt raised to the power of 1 minus alpha, where ot is the output in period t and ct is the capital stock in period t. So per capita output is given by ot by nt is equal to act raised to the power of alpha into nt raised to the power of 1 minus alpha all over nt, which is equal to act by nt the whole raised to the power of alpha, or ot is equal to act. Let S be the fraction of income saved by the consumer. Let ST be the savings and KT be the consumption. Then ST is equal to SOT and KT is equal to 1 minus SOT. That is, OT is equal to ST plus KT. Now let NO be the initial population size. Then NT is equal to 1 plus N raised to the power of T NO. By the assumptions, all savings must go in investment, that is IT is equal to ST, where IT is the investment in time period T. CT plus 1 is equal to 1 minus RCT plus IT, where R is the depreciation rate. Substituting the values for IT in terms of ST and corresponding related variable CT and NT, we get CT plus 1 is equal to 1 minus R into CT plus S A CT raised to the power of alpha NT raised to the power of 1 minus alpha, or CT plus 1 divided by NT is equal to 1 minus R CT divided by NT plus S A CT raised to the power of alpha into NT raised to the power of 1 minus alpha divided by NT, or NT plus 1 by nt into ct plus 1 by nt plus 1 is equal to 1 minus r ct divided by nt plus s a ct raised to the power of alpha divided by nt raised to the power of alpha, or 1 plus n ct plus 1 is equal to 1 minus r ct plus s act raised to the power of alpha, or ct plus 1 which is equal to 1 minus r by 1 plus n ct plus sa divided by 1 plus n ct raised to the power of alpha, which is the first order non-linear difference equation. In equilibrium, per capital growth can be evaluated by ct plus 1 is equal to ct is equal to c star. Substituting in the above model, we get c star is equal to SA divided by n plus d 1 divided by 1 minus alpha. Correspondingly, in equilibrium state, income, consumption, saving, and investment can be calculated using the value of C star in O star equal to A C star raised to the power of alpha. I star is equal to S star, which is equal to S into O star, and K star is equal to 1 minus S into O star.
Let us now summarize what we have learnt in this module. First, a general non-linear difference equation of first order is of the form: first, f xn plus 1 comma xn comma n bracket closed is equal to 0, or second, xn plus 1 is equal to fxn, where f is a non-linear function. Second, a fixed point is said to be one stable if f prime x star is less than 1. Second, unstable if f dash x star is greater than 1. For f dash x star equal to 1, further analysis needs to be done. Third, the convergence or divergence in steady or oscillatory form is determined by the algebraic sign of slope of function f. Fourth, if fxn is less than 1, time path converges steadily to equilibrium value without oscillation and diverges if fxn is greater than 1. If f prime xn lies between -1 and 0, time paths oscillate and converges to equilibrium and diverges from the equilibrium value if f prime xn is less than -1. Fifth, non-linear equations of particular types can be changed to linear difference equation by using suitable transformation.